Hi, my name is Chelsea Bovell, and I'm going to be discussing my final project for cosmology. I did research on dark matter, and the aim of the project was really to explore as much information as possible about what we know currently concerning dark matter. So I looked into what some theories about its composition were, candidates for its composition. I looked into the size and other theories we have about what dark matter is made of. And then I also wanted to sort of summarize the new research that's been happening. Research that tries to figure out where dark matter is, and research that tries to simulate dark matter and its effects on the cosmos. And then finally, I wanted to talk about some alternate theories of dark matter, to dark matter. So first, I explored the current evidence for dark matter. So we have indirect evidence from gravitational lensing. We get evidence from the orbital velocities of celestial objects, and then we have the most pressing evidence, which is that we have these galactic halos with large mass-to-light ratios, meaning that galaxies are emitting less radiation than expected considering the high mass volume. So there's something there that we cannot detect but still has a slight pull. And scientists found that there's a subcritical universal mass density after they calculated the baryonic fraction to be 15%. And research about the cosmic microwave background also reinforces the justification for this idea of dark matter. So there are a few theories about its composition. We know that since dark matter weakly interacts with matter, it's non-baryonic. So two candidates include neutrinos, which are a form of hot dark matter, and WIMPs, which are weakly interacting massive particles. The theory that fits the current model of the universe best is known as the lambda-CDM model, but most of the characteristics of this cold dark matter particle are unknown. It's theorized to be likely smaller than the smallest known particle, but one paper I read did say that it's neither ultraviolet nor massive to the point where it's as big as one solar mass. And then another paper talked about making approximate assessments of dark matter's size. So there are some potential sizes. And it used the idea that quantum gravity will eventually cause any substance to decay, and gravity will couple to all particles at some point. Next, I talked about finding dark matter. So one of the most interesting studies I found published a new way to find dark matter using the effects of weak gravitational lensing. So this particular study strayed away from the use of traditional weak lensing and instead used precision weak lensing to view galaxies and their dark matter halos more clearly. The basic idea with precision weak lensing is to use galactic velocity fields to measure the lensing effects. So since galaxies will always follow a pattern of circular motion and this is predictable, it can be said that the unlensed galaxy will have a velocity that is symmetric about the axis. And then at its highest and lowest points, the velocity gradients will be orthogonal. So weak lensing cuts into these images tangentially and makes a shear in the axis symmetry. And it's able to find the lens mass based on the disruption of the axis symmetric velocity. So after measuring the distortion of the galaxies from their real images, the researchers were able to predict the quantity of dark matter needed to cause that distortion. A powerful and complex simulation of the universe called The Last Journey was one of the topics in my paper. So this simulation modeled 1.24 trillion particles in the galaxy, and it was completed on a supercomputer named Mira. And the goal of this experiment was really to catalog the skies with extreme attention to detail and also to map out the galaxies so that the scientists could survey their dark energy and dark matter content. This simulation was based on the lambda-CDM model as well, and it made use of the 6 cosmological constants and oscillated those values. There are many alternative theories of our galaxy. And in one theory, a researcher named Ludwig suggested that we actually have a gravitomagnetic field causing a slight pull rather than dark matter being responsible for this. And it also, gravitomagnetism provides the shape profile and mass distribution of galactic disks. Thank you for your attention. This was a brief summary of my final project for cosmology.